In this example, we're going to look at how to use the method of Lagrange multipliers to find the radius and height that maximize the volume of a closed cylindrical container with a fixed surface area equal to 48 pi. So for a problem like this, the first step is to come up with the equation of the function that you'd like to find the extreme values for, and equations for any constraints on your variables. So here, the function that we'd like to maximize is the volume of the cylinder, and we'll have a constraint related to the surface area, specifically that it has to be equal to 48 pi. So let's write down these functions. So just to give us something concrete to visualize, let's draw this cylinder, and let's label the height by h, and the radius by a little r. So the volume of this thing we can write down as a function of r and h, and it's just equal to the area of the base, pi r squared, times the height. The area is also a function of the radius and the height, and it's equal to the sum of the areas of the bottom and the top, plus the area of the lateral face. So the bottom has area pi r squared, and we've also got the top with the same area. So we'll have 2 pi r squared from the top and bottom. And then the lateral face is basically a rectangle that's been rolled up. It's going to have length equal to the circumference, 2 pi r, and height equal to h. So that's 2 pi r times h. And this is actually a constraint, that this function is equal to 48 pi. So we've got our equations now. We can go ahead and apply the method of Lagrange multipliers. And in this context, we're basically going to be saying that the gradient of v is equal to some scalar multiple, our Lagrange multiplier lambda, times the gradient of the area. For our gradient of v, we're going to need the partial derivative of v with respect to r. That's 2 pi rh. And the partial derivative of v with respect to h is pi r squared. Partial derivative of a with respect to r is 4 pi r plus 2 pi h, and the partial derivative of a with respect to h is 2 pi r. If we write our equation relating the gradients in component form, it looks like 2 pi rh pi r squared is equal to lambda times 4 pi r plus 2 pi h, and then 2 pi r. This basically gives us two equations. First, 2 pi rh is equal to lambda times 4 pi r plus 2 pi h, and pi r squared is equal to lambda times 2 pi r. Looking through this, we've got pi's on every term, so we can basically ignore those and get a simpler set of equations after that. Don't forget, we should also think of this constraint equation up here as being another equation that we can use to solve for r, h, and lambda. So if I were to number these, I could say this is equation 1, equation 2, and let's call this equation 3. So equation 2 only has r and lambda appearing, so this means that we'll be able to solve for r in terms of lambda. That seems like a useful thing to do, so let's do that. Having canceled out the pi's, we get r squared is equal to 2 lambda r. One solution to this equation is that r is equal to 0. But if we set r equal to 0, we're going to get a cylinder with 0 radius, which has 0 volume, and so certainly this is not the optimal radius for maximum volume. So we can safely say that r is not going to be equal to 0, and divide both sides by r to get r is equal to 2 lambda. Now let's plug this into equation 1, replace every instance of r with 2 lambda, and we'll be able to solve for h in terms of lambda as well. So equation 1 gives us 2 times r, which we now know is equal to 2 lambda, times h is equal to lambda times 4 times r, but r is 2 lambda, plus 2 times h. Tidying this up a bit, we get 4 h lambda is equal to lambda times 8 lambda plus 2h. Again, we have a solution here where if we just set lambda equal to 0, the equation is satisfied. But since r is equal to 2 lambda, setting lambda equal to 0 would be equivalent to setting r equal to 0, which we've already argued we don't want to do. So we can safely say lambda is not going to be equal to 0 and cancel one factor of lambda from each side. This then gives us 4h is equal to 8 lambda plus 2h, or h is equal to 4 lambda. So we've got r and h both in terms of lambda now. We can now use our constraint to figure out what lambda should be. Remember, our constraint says 2 pi r squared plus 2 pi rh is equal to 48 pi. Let's cancel out those pi's. And then let's replace r with 2 lambda and h with 4 lambda. This gives us 2 times 2 lambda squared plus 2 times 2 lambda times 4 lambda is equal to 48. Or 8 lambda squared plus 16 lambda squared is equal to 48. Or lambda squared is equal to 2. Solutions to this are lambda equal to plus or minus root 2, but since the radius and height are both proportional to lambda and are both strictly positive, we only need to worry about the positive root here. And we're basically done now. Since we've worked out what lambda is, we know that r is equal to 2 lambda. We get r has to be equal to 2 root 2, and h is 4 lambda, so h is 4 root 2. And those will be the optimal dimensions for maximizing the volume of the cylinder with the particular given surface area. So we're finished the problem, but one thing I'd like to note here is that the area I picked here is somewhat arbitrary. I picked 48 pi just to have a number to work with, but whatever area we had chosen, we would have got that r is equal to 2 times the Lagrange multiplier and h is equal to 4 times the Lagrange multiplier, which is basically saying that the height should always be twice the radius to maximize the volume of the cylinder. And that will be true whatever area you pick. Alright, so that's it for this example. I just wanted to show you how to use Lagrange multipliers to solve a real-world optimization problem. Thanks a lot.